Okay. So last week, the first, I don't know, 20 minutes at least was spent motivating the study of elliptic curves in modular forms. I'm not going to go through any of that. If you want to see any of that, I'll be sending my notes out at the conclusion of this series of talks. I'm not going to do it before then because I'm going to be modifying and fixing things in between now and then. But we also defined what a congruent number is. So without loss of generality, a square-free natural number is congruent if it's the area of a right triangle with rational side lengths. And we're interested in a set of conditions that are checkable and terminating, preferably quickly, that determine whether or not a given natural number is congruent. And if you just kind of think about this naively, you'll understand that if you don't come up with such conditions, then you have infinitely many triples of rational numbers to check. You have to make sure they form a right triangle and that their area is n. And this seems like a daunting task. So the first thing we discovered is, and this is kind of one of the older theorems about congruent numbers, is that if I take a square-free natural number and then three rational numbers, x less than y less than z, then right triangles with leg lengths x and y and hypotenuse z and area n are in bijection with real numbers x, such that x and x plus or minus n are squares of rationals. In the language of congruent numbers, what that means is n is congruent if and only if there exists a real number x, such that x and x plus or minus n are squares of rationals. As a matter of fact, while I didn't prove this, here's the correspondence right here. I mean, you can just check that this works. It's not very hard to check. And then what we saw by doing some algebraic manipulation is that there's a correspondence between right triangles with rational sides with area n and certain points on the elliptic curve y squared equals x cubed minus n squared x. We checked this is an elliptic curve. We defined what elliptic curves are. Elliptic curves are equations that can be written in the form y squared equals, let's say, ax cubed plus bx plus c. Okay, and such that the cubic on the right-hand side has distinct roots, which we saw as the same thing as being smooth. So basically smooth cubics written in a certain form. And the reason that we want them to be written in that form, well, it's not really a matter of what we want. It's a matter of the fact that you can change any cubic in two variables into an equation of this form. Okay, so we're right about here now. There's the correspondence between basically congruent numbers and there's the side lengths of their triangle, the rational side lengths, and certain types of points on this elliptic curve here. What types of points? Here's the proposition up here. So if x is the square of a rational, or I should say x is the square of a rational and has even denominator if and only if there's a right triangle with rational sides and area n corresponding to x under this correspondence up here. So the next natural step is, well, maybe we ought to study this curve. We know it's a special type of curve. We know it's an elliptic curve. I told you last time all kinds of special properties elliptic curves have. So maybe we should try to apply some of those special properties to our situation and see if we can figure out how to proceed, because this is still not a very checkable condition for whether or not a square-free natural number n is congruent. I mean, checking whether or not this curve has a rational point on it such that the x coordinate is the square of a rational with even denominator is still not very checkable. So we have to keep going. And so then we did all this, and then I think we started to talk about elliptic functions and lattices last time. So we took a lattice in the complex plane, and I showed you what that was. That's just all integer linear combinations of two linearly independent vectors in the plane. And then we looked at its fundamental parallelogram. So if you weren't here, I'm going to recall what that looks like. If I take my lattice, okay, ostensibly it looks like this somehow, okay. There we go. But mod and equivalence relation, really all that matters is this parallelogram here. Okay, and everything inside of it, let's say. So this guy here is the fundamental parallelogram, which we call capital pi, for the given lattice given by the orange dots. Okay, everything is sort of determined by this parallelogram. And what we said is we're going to look at special types of meromorphic functions on the complex plane, the so-called elliptic functions relative to the lattice. You also see them often called doubly periodic functions. Why? Because what's the definition? A meromorphic function on the complex plane is elliptic relative to a lattice if f of z plus L is f of z for every point in the lattice. So what that really means is if you look at the fundamental parallelogram, function values on points that are opposite in the fundamental parallelogram are the same. Okay, and that works with both sides here. So the pink points here would have the same function value if f was elliptic relative to this lattice, but the blue points would also have the same function values because they're also identified on opposite sides of the parallelogram. And then I think I ended with this statement right here. I said you should think of elliptic functions as meromorphic functions on a torus. And we saw why that is. Why is that? Well, if we're requiring that points on opposite sides of the parallelogram just be identified or have the same function values, then we might as well identify those points. But if you identify points on opposite sides of a parallelogram, maintaining orientation as you do so, what do you get? You get a torus, right? So you can actually think of, when I say elliptic function, you can think of meromorphic functions on a torus. Okay, and I think that's right about where we stopped. So today what we're going to do is we're going to study this this set of elliptic functions for a lattice, and we're going to see what we can get out of it. We're going to call epsilon sub L the set of elliptic functions for a given lattice L, and you can check that this is actually a subfield of meromorphic functions, so it's closed under all the field operations, but it's also closed under differentiation. Okay, so this is not hard to check, and I would encourage you to do so. So what should we want to do next? Well, if we're going to think of these as meromorphic functions on the torus, then what we should be after is the simplest meromorphic functions on the torus. And how would we quantify simplicity for meromorphic functions? Maybe like the number of poles or the order of the poles, something like that. So you might ask, well, are there any holomorphic functions that are in the field, the epsilon sub L? Are there any with these functions that don't have any poles? And you can prove, I'll even leave this is easy. I'll leave it as an exercise that every elliptic function with no pole is just constant. And so we're not particularly interested in those. Okay. So if functions with no poles are not interesting, what about functions with one pole? Well, there's another proposition you want to be aware of here. So let's suppose I translate my parallelogram over a little bit by some alpha. Maybe I move it over just a touch by alpha. I mean, it doesn't matter. I can move it wherever I want. But let's say I translate it by alpha just a little bit. Now, so let C be the boundary of the translated parallelogram. Okay. And let's suppose that we have an elliptic function that has no poles on that boundary. Okay. Then, using the residue theorem, you can show that the sum of the residues of F inside that translated parallelogram is 0. Okay. And then if you put these two propositions together, and again, I'm not going to prove any of this, but you can check it yourself. If you put them together, what you get is every non-constant elliptic function has to have at least 2 poles. So no poles is not interesting because we just get the constant functions. These two propositions mean, in particular, proposition 4 here really means you're not just going to have one pole. So you're going to have at least 2 poles. So if the number of poles or their orders or something like that is our measure of the simplicity of an elliptic function, then we should be looking for the simplest elliptic function with 2 poles. Okay. So before I tell you what kind of the big, very important elliptic function is, there's one more proposition I want you to be aware of, and it's this proposition 5 here. So let's say, again, that I've translated my parallelogram over a little bit. Maybe I translated it down here. Who cares? Okay. And again, let's suppose F has no zeros or poles on the boundary of my translated parallelogram. Okay. If you look at the order of all the zeros and the orders of all the poles that are inside the translated parallelogram, then the sum of the orders of the zeros equals the sum of the order of the poles. Okay. So this is a very complex analytic sounding statement that you might remember something similar from, like an introductory sequence on complex analysis. Not order of poles equals sum of the orders of poles equals sum of the order of zeros. But this, we're applying this now to basically to complex tori. Okay. So we will need this in a second. And I'm going to give for you now a very special elliptic function called the Weierstrass phe-function. And this function is basically going to do a whole lot of damage for us. So here's the function. It's relative to a lattice. So we call it phi of zl. And what it is it's 1 over z squared plus the following sum. You're going to sum 1 over z minus l squared minus 1 over l squared. And what are these l's? The l's are all the non-zero points of the lattice. So all these orange points up here, but not the origin. Okay. Mainly because you can't really, I mean, this is not even defined at the origin. So you can check pretty easily if you'd like to, I guess, exercise. First thing you have to worry about when you got a nasty sum like this is, does it actually converge? How does it converge? It converges absolutely and uniformly on any compact subset of C minus the lattice, which is exactly what we want. So it will end up being a nice meromorphic function for us. And is this guy one of these nice, simple two-pole elliptic functions? That's the next question we want to answer. And so proposition, not only is the Weierstrass phe-function actually an elliptic function, but it has only one double pole, and that pole at each lattice point. So if we imagine the fundamental parallelogram as a torus, what is that saying? That's saying that the phi function is an elliptic function with one double pole. Why only one? Because these 4 points of the parallelogram have been identified, okay, as one point. And those are exactly where the function has a double pole. So it seems like we've located an example of a non-trivial elliptic function that has a double pole. And so it seems to fall into this nice class of simple elliptic functions up here. And why do we care about this function? Well, here's the key point here. If you take any elliptic function, okay, then we know that the field of elliptic functions is closed under differentiation. Well, we know the Weierstrass phi function is elliptic, so that means its derivative is also elliptic, right? It turns out any elliptic function is a rational function in phi and phi prime. So you can show this using a combination of the above propositions, right? So in some sense, phi is the building block for epsilon sub L. Well, really phi and phi prime, but phi prime comes from phi, so.
So could you say any more on the proof of proposition 8, or if you don't, or unless you don't want to say it, then it's fine.
Actually, I think it's not super easy.
Okay.
Let me, you're actually reminding me of something though. I need to pull one thing up. There's one thing I had in front of me last talk, and I want to have it in front of me this talk too. Blah, 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 blah.
Yeah, it's probably not completely trivial, I think. Anyway.
No, I'll tell you something. Just let me pull this up anyway. In fact, I could just pull it up in my notes that I took, but I'm not going to. It's one of those things where I'm not going to remember off the top of my head. Okay, I'm almost there. Oh yeah, no, it's not so easy to show, actually. If it was quick, I would run through it, but it looks like it's some work. Yeah, yeah. So yeah, if you guys do want to see proofs of things, just let me know. I have the proofs of everything I'm saying to you. I just probably won't go through anything if it's kind of a longer proof, and this looks to be one of them. You basically play around with the fact that these functions are even and odd respectively, and use the above propositions and the residue theorem and stuff like that. So speaking of that, you can check easily. This is easy to check. The Weierstrass phe-function is an even function. You can actually see that sort of explicitly from its form, but you can prove it rigorously, of course. So what that means is the derivative is an odd function. And so if you actually take epsilon sub L and you look at the subfield of even elliptic functions, okay, you know that forms a subfield, first of all. You can show that's generated by phi. So somehow every even elliptic function is sort of built with phi. And then if you put all of this together, everything I've said so far together, you come to the main result here. And it's actually, even though it's sort of the most important result we need from this section, it's easy enough that I'll even leave it as an exercise. Once you have everything above, it's not that hard to show. You can show that phi prime squared, which you know is even because phi prime is odd, is actually a cubic in phi. And that's going to be huge for us, as we will see coming up. So that's the end of this little section here. Are there any other questions I can take on just elliptic functions?
What references did you use for this section?
Most of this talk is going to come from Koblitz's book. Not all of it, but all of it so far, except for the motivation and introductory stuff. So Koblitz's book is Introduction to Elliptic Curves and Modular Forms.
All right.
And as we get further into the talk, though, there will be other references that I use, and I will give you those if you guys want those too. Yeah, he proves this. All of the stuff I've said so far is proven in there. Okay, anything else? So we've got a handle on this statement right here. Phi prime squared is a cubic in phi. Okay, who cares? Well, another thing you can check is this. So you can actually find the zeros of phi prime pretty easily. You can show that there are 3 of them and that they are simple. So they are order 1 zeros. And here are the zeros. Row of W1 over 2, row of W2 over 2, and row of W1 plus W2 over 2, where what are these W1s and W2s? They generate our lattice. Okay, so they're the vectors in the complex plane that spawn the lattice. It's not hard to show these are the zeros of phi prime. And it's also not hard to show that they're distinct values, which is going to be important, right? Because why do you think a statement like this is going to be important for us? If phi prime squared is a cubic in phi, that sounds like maybe an elliptic curve type statement is coming up. And if we want that to truly be an elliptic curve, the zeros of phi prime had better be distinct, right? Or else we're not going to have that smoothness we want from the definition of elliptic curves. So let's look at this. So from above, we know phi prime squared is a cubic in phi. And the zeros of the right-hand side must be the zeros of phi prime, right? In other words, here's what the cubic has to look like. It has to look like C, some constant, times phi minus E1, one of the zeros of phi prime, times phi minus E2, another one of the zeros of phi prime, and phi minus E3. the final zero of E prime. By the way, I can also, just so you have a visualization to go with these zeros, let me draw the fundamental parallelogram again. And let me just go ahead and actually put those zeros on the parallelogram so you can see them. Let's just do this black here. So if I call this guy W1, this first vector here, and this guy omega 2, or W2, then this orange dot out here is W1 plus W2. So where are these, where do W1 over 2, W2 over 2, and W1 plus W over 2 live? Well, they just live at the halfway points of kind of in the center of the parallelogram and then on the center of each of the sides. And once you identify all the sides to make your torus, this side will be identified with this side. So you'll have a single point on your torus as one of your zeros, and then two other ones. Okay, because these horizontal sides will also be identified. And then this middle guy will just be somewhere on the torus. So those are the three places in the parallelogram where the zeros come from. And row of those points, of those red points, those are the zeros of row prime. Okay, so we've got our cubic here. And so, like I said already, you can notice this is a complex elliptic curve. How do you notice that? What you do is you say, I'm going to let y be phi prime, and I'm going to let x be phi. Then this turns into the following equation. Y squared equals c x minus e1 x minus e2 x minus e3. And because these three roots are distinct, which you can check, this constitutes an elliptic curve by our definition. Okay, so the only thing would be, what is this constant here? You can check it's 4. Okay, so c must be 4 here. And so what we have is the following nice succinct relationship on the elliptic function phi and its derivative. Phi prime squared is f of phi. And what is this f? It's this cubic here, 4 times x minus e1 times x minus e2 times x minus e3. As a matter of fact, you can do better than this. You might also ask not only what is this constant here, but when I expand this all out, it's going to have a certain form, right? It's going to have like maybe an x squared coefficient, an x coefficient, and a constant coefficient. What are those coefficients? Well, it takes a little bit of work to show that you get the following. This cubic can actually be written as 4x cubed. So that's obvious, right? Because when we expand this out, we'll get x cubed times 4. You won't get any x squared coefficient. And then you'll get an x coefficient and a constant coefficient. And those coefficients are given by negative g2 of L, insinuating that this coefficient depends on the lattice, and negative g3 of L, also depending on the lattice. And here are the expressions for those coefficients. So g2, for example, is 60 times this infinite sum over the lattice of 1 over L to the 4th. And g3 is 140 times the same sum of 1 over L to the 6th, where L ranges through the non-zero lattice points. And you can check both of these sums converge absolutely, so there's no problem. And this guy right here is called the Weierstrass normal form of our elliptic curve. More generally, ax cubed plus bx plus c equals y squared is the Weierstrass normal form. But in the case you're working with complex elliptic curves like we are, this specific expression is called the Weierstrass normal form, where g2 and g3 are known. Okay. And any elliptic curve, like I told you guys last time, can be written in a similar form. So when an elliptic curve comes from a lattice, you can always write it like this. And we will see later, actually, okay, I'll spoil it. We'll see later, actually, that every elliptic curve comes from every complex elliptic curve comes from a lattice. So the converse to this is kind of true as well. So every lattice admits an elliptic curve, and every elliptic curve is admitted by a certain lattice. So let's look at the following very special map now. We're going to take C mod the lattice, and we're going to map it to the projective plane. And what is that map going to look like? Well, what do points in projective plane look like? They have 3 coordinates, if you remember from last time. And 2 points are equal here if and only if their coordinates are non-zero scalar multiples of each other. So for example, x, y, z is the same thing as 2x, 2y, 2z. The only other thing we have to remember is 0, 0, 0 is not a point here. At least one of the coordinates has to be non-zero. And the naive reason for that is like points here are lines in the affine space above through the origin. But there is no line through the origin corresponding to the origin itself. Okay, so that's why 0, 0, 0 is not present here. And here's the map. We're going to take a complex number, or a coset of a complex number rather, and we're going to send it to the following triple. Phi of z, phi prime of z, 1. Okay. And that's going to be what the map is if z is not 0. If z is 0, we're going to send 0 to the point at infinity, which we discussed last time, which is the point 0, 1, 0. Okay. Okay, so big, huge proposition coming in here. This map is a biholomorphism from C mod L onto the projective version of this elliptic curve we just defined above. And so what that means is every complex torus is biholomorphic to a projective complex elliptic curve. And in fact, we'll see more than that is true soon. We'll see they're also group isomorphic. So that's the end of that section. So you can think of like the complex plane modulo a lattice as just a projective elliptic curve up to biholomorphism. And like I told you, if you start with the elliptic curve, you can actually go backwards as well. You can find a lattice that gives you in Weierstrass normal form the elliptic curve you started with. And since every elliptic curve can be written in Weierstrass normal form, you've basically sort of described all complex elliptic curves in terms of lattices. Okay. So are there any questions on this part? Let me just okay. Now, some of you may have heard that there's an addition law for points on the elliptic curves. We're going to need to discuss that. So we're going to do that now. We would like to bolster our understanding of this biholomorphism above here. Okay. In particular, we would like to turn it into some kind of group isomorphism as well. Because here's the thing, C mod L has a stupid addition law on it, right? You can just do addition mod L. Like if I take Z1 plus L and I add it to Z2 plus L, well, I can define that to be Z1 plus Z2 plus L. And you can check this as well defined, there's no problem. So there's an addition law over here. So we wonder, is there some way of taking the addition law there on C mod this lattice, okay, and which we can think of as a torus, by the way. It's like the fundamental parallelogram with the opposite sides identified. So can we take the addition law on our torus and can we transport it over to the elliptic curve that's over here? And the answer is yes. So what would you do? Like, how would you define that? Well, so let's say I have 2 points on my elliptic curve. Gosh, I didn't leave myself very much room here. So I have 2 points on my elliptic curve. Let's call them P1, P2. Okay, those come from 2 points in my torus, right? Z1 and Z2, let's say. Okay. Now, what does it mean that they come from Z1 and Z2? That means that, I guess I'll go over here. That means that P1 is given by phi of Z1, phi prime of Z1, 1. Let's assume for a second Z1 and Z2 are not 0 so that we don't have to worry about the point at infinity. Okay. Right? And then P2 is phi of Z2, phi prime of Z2, 1. Again, assuming it's not the point at infinity. So what should I define P1 plus P2 to be on the elliptic curve? I'll just define P1 plus P2 to be what? I mean, you're never going to guess. Phi of Z1 plus Z2, phi of Z prime, phi prime of Z1 plus Z2, 1. Okay, unless the sum happens to be 0, then I'll just send it to the point at infinity anyway. Okay. So, so this is kind of problematic though, right? So there's two problems with this definition of addition on the elliptic curve. The first problem is, what does this actually look like geometrically? This is a very analytic way of describing it, but what does it actually look like? Like if I give you a picture of the elliptic curve and 2 points on it, can you draw the third point? Can you draw the sum? It turns out you can, okay, which I'll show you how to do. But there's another problem, right? The other problem is this. Purportedly, if I give you 2 points on the elliptic curve, I'm going to give you their coordinates, right? And let's say we're working in the affine kind of projection of the curve, so we're not worrying about the point at infinity. Then I'm drawing an actual literal elliptic curve, okay? I'm giving you 2 points on it and their coordinates. They're going to be x, y coordinates. Can you give me the coordinates of the sum of those 2 points without transporting your addition back to the lattice and then mapping back to the elliptic curve? Because if you have to get the coordinates of the sum by mapping back to the lattice every time and coming back, that's going to get really annoying really fast. Not only is that going to get really annoying, what if I give you an elliptic curve that you don't know it comes from a lattice, because right now we don't actually know every elliptic curve comes from a lattice, or you don't know which lattice it comes from? Well, then you're not going to actually even be able to take these points and map them back to a lattice. So what, are you just toast? Are you not going to be able to find the coordinates for the sum because you don't know the lattice? No. We have to fix that. Okay, so one thing that's good about this addition law is that it is a well-defined addition law. In particular, there is an additive identity, which I'll leave to you. You can check that's just the point at infinity. And from now on, we're going to denote the point at infinity by 0. Okay. So check that when you add any point to the point at infinity, you get 0. This is not hard to check, right? So what that means is like p plus 0 is always p for all p in the elliptic curve. Okay, and same for 0 plus p. Where 0 is the point at infinity, which has coordinates in projective space 0, 1, 0. Okay, so that's fine. We now have an additive identity. Fair enough. The next thing you want to do is you want to say, okay, let me take 2 points on the elliptic curve, and let me assume that they have the same x coordinate but have different y coordinates. Well, what are we looking at graphically here? If you graph a generic elliptic curve, then because of its Weierstrass normal form, you can see there's going to be this symmetry about the x-axis. So you're going to get something kind of like this, and there might be some second component over here, like some kind of loop or something. It depends on the discriminant. But graphically, what are these 2 points representing? They have the same x coordinates, right? But different y coordinates. That's what we're saying. So this is like P1, and this is like P2. Okay. Now, phi prime is an odd function. We talked about that above because phi is even. And because of that, you can check that this is going to actually force the situation y1 equals negative y2. I mean, I gave you, pictorially, you might say that's obvious. Well, you can't do proof by picture in math, not usually. So you want to know that whenever you have 2 points on an elliptic curve with the same x-coordinate that are different, y2 must be negative y1. And it turns out that is the case because phi prime is odd. I'll let you check that. Easy check. Okay. In fact, I put a little hint here. What happens if phi of z1 equals phi of z2, but the derivatives differ? So, okay. If you transport this information back to the plane, back to the complex plane or the torus, what you find is that z1, the point that mapped to p1 under this correspondence up here. So let me write that. And then z2, the point that mapped to p2 under the same correspondence up here. You can see that z1 has to be negative z2. And that's because you can easily see that the only values which are the negative of each other, only values which are the negative of each other can have the same phi value, basically because phi is an even function, okay? But then what is, in this case specifically, what is p1, what will p1 plus p2 be? Well, if z1 is just negative z2, then p1 plus p2 will come from z1 minus z1, which is 0. Well, that just means p1 plus p2 is the point at infinity, which means p1 is the inverse of p2. So points like this, they are actually additive inverses of each other. Okay, so in this picture, p1 plus p2 is 0. That's just in this setup though. But we're building like we're slowly building this addition law, okay? So what I wrote here, a good concise way of thinking about it is 2 points on the same vertical line are additive inverses, okay? And when people are doing the addition law, a lot of the times what they like to do is they like to sort of imagine the point at infinity as temporarily living on the x-axis, just so that they can view adding these 2 points as like collapsing them down to the point at infinity. And then you can just move this orange point around as you see fit. I mean, I don't do that, but there are people who do that, okay? Another way of thinking about it is, well, no, I won't spoil that. Never mind. Okay, what if p1 equals p2 and both of them are on the x-axis? Well, by the above discussion, so maybe we're over here. By the above discussion, both of the y-coordinates are since both of the y-coordinates are 0, what you will also see in this case is that p1 plus 2 is still equal to 0. Okay? So in all cases, 2 points on a vertical line are additive inverses of each other, even if those points are the same point. You can view this vertical line here through the purple point as like a vertical tangent line to the curve. Okay. So summarizing the entire discussion on these types of points, if I give you x, y on the elliptic curve, the additive inverse is x negative y. All right. Which still isn't fully telling us how to actually do this addition law, but we'll get there. I'll show you how to do it geometrically. So next, what you can observe is the following. Let's say I have two points on the elliptic curve, neither one of them the point at infinity, neither one of them the additive identity, okay? Okay, so let's draw this. I'll just use the same kind of, well, I'll put a little second component over here, just because. So let's say that's my elliptic curve. Okay, let me take 2 points. Okay, P1 and P2. Now, what do you notice you can always do? You can always join them with a line, right? So let's do that. So we join them with a line, great. What if P1 equals P2, by the way? If P1 equals P2, then we'll say that the line joining them is the tangent line to the curve. So like if I'm over here, then here's the line joining them. Okay. Something like that. Now, we already know that if this orange line is vertical, then P1 and P2 are additive inverses of each other. And I think I just called both of these P2. So let's fix that. Okay. So let's suppose the line is not vertical. Let's suppose this orange line is not vertical, because if it is, we sort of already understand how to add the 2 points together. We add them, we're just going to get 0. We're going to get the point at infinity. Okay, so proposition. Let's suppose the sum of P1 and P2 is P3. Then it turns out negative P3 is the third point of the intersection of the elliptic curve with L. Okay, is the third point of intersection of the elliptic curve with L, where L is this line. Now you might say, first of all, what the heck did you just say? What does that mean? Second of all, how do you know there's a third point of intersection? Well, that comes from algebraic geometry. There's a theorem called Bazoot's theorem. It's a very special case, but this third point of intersection is guaranteed to exist. When you intersect a line with a cubic, you're going to get 3 points of intersection counting multiplicity. Okay. So this comes from Bazoot's theorem, which is something you don't even need scheme theory for it. You can learn it from an undergraduate level textbook on algebraic geometry. So if you're interested in learning that, let me know. So that third point has to exist, okay? And what is this saying geometrically? This is saying that if I want to do P1 plus P2 and the line joining them isn't vertical, how do I find P3, the sum? I take that line joining them, okay? Then what I do is I find the third point of intersection with the curve. Okay, so this picture is really bad, actually. I find the third point of intersection with the curve. In this case, that would be this point right here. The point opposite that point across the x-axis is the sum of P1 and P2. So let me draw a better picture. I don't really like this picture that I've managed to draw here. Yeah, so let's actually draw the same type of elliptic curve, but I'll choose 2 other points because my sum wasn't very interesting there. Okay, so we'll take these 2 points, P1, P2. How do I find the sum? This proposition says draw the line through them till you hit the third point on the elliptic curve. And what are you going to get? You're going to get negative P3. That's what the proposition says. But how do you get negative P3 from P3? We just discussed that above, right? You take the vertical line through negative P3, and you find where it hits the elliptic curve symmetrically across the x-axis, and that'll give you P3. So this is the addition law, okay? And this works even if the 2 points are the same, even if these points are tangent or are the same and you're using a tangent line, there'll still be some third point of intersection, and its mirror image across the x-axis will still be the sum. And again, you don't have to worry about this third point existing because algebraic geometry. Okay. And I want to remark, this actually, what I just described works for any elliptic curve, because we'll see later that every elliptic curve comes from a lattice. So there's always an addition on a torus that the addition on the elliptic curve comes from. So you never have to worry about this actually failing for some elliptic curve because maybe you think that elliptic curve doesn't come from a lattice. By the way, this I'll label that P3. Okay. Okay. So we know how to add points on elliptic curves. Now there actually is one other remaining problem with this addition law, and it's subtle. The problem is it's actually not obvious this is associative. And in order for this to be a group law, it has to be, the addition has to be associative. That's actually not very easy to check. So if you would like, you can check this as associative. But I'll tell you that the reason it's so hard to check this as associative is because we're building the group law from the wrong perspective. We're building it as coming from a group law on a complex lattice, but there's a better way of doing it. You can view the group law as coming from the group of a certain type of sheaves on this elliptic curve. If you view it as a scheme, you can view the group law as coming from that group. And in that group, associativity is obvious. And the fact that this group law that we just came up with is associative follows trivially from that. Whereas from this perspective, like if I just tell you this right here is the group law on the elliptic curve, it's not easy to convince yourself just by drawing pictures that this thing actually is associative. But you can check it. You don't need the algebro-geometric perspective to see that. There is a proof, a classical proof that this is associative. And I would encourage you to look that up. If you want another exercise, remember, what elliptic curves are we looking at? Here are the elliptic curves that came up in the congruent number problem. Y squared equals x cubed minus n squared x, where n is a square-free integer, natural number. So you might ask, does this elliptic curve arise from some lattice in the complex plane? And the answer is yes. And in some sense, it arises from sort of the most nice lattice you can have. It's just actually a multiple of the Gaussian integers. So you can check that. Okay, complex multiple of the Gaussian integers. Actually, I think it's a real multiple. And so let me conclude with this. I had two goals when I started talking about this group law. The first goal was, could I describe it geometrically? And I've done so. Okay. The second goal was, can I get the coordinates to the third point without going back to the lattice in the complex plane, without going back to my torus? And the answer is yes. And here are the coordinates. And you can show this pretty easily. The proof of this follows just from the geometric description of the law. But let's say P1 has coordinates x1, y1. And let's say P2 has coordinates x2, y2. And let's say the sum is P3. And let's say that has coordinates x3, y3. Then if the right-hand side of your elliptic curve looks like ax cubed plus bx squared plus cx plus d, here are the coordinates for x3. And here's the coordinates for y3. In terms of nothing but x1, y2, x2, y2, a, b, c, and d. And what else? That's it. Why are there two different formulas for x3, you might ask? Well, because there's two different cases. The first case is P1 and P2 are distinct. The second one is P1 equals P2. Okay, which is why this derivative shows up like a slope of a tangent line showing up. Okay, and then M down here is just whatever's inside the parenthetical. So there's also two formulas for y3 here. They depend on which situation you're in. And the difference is this M here. There's two different M values. And again, this is just a straightforward computation once you know how everything works geometrically. Okay, the real thing to prove is that this is the group law geometrically. Once you've shown that, the algebraic, the formula for the coefficients is nothing to show. Okay. And so I think that's a good place to stop. That time kind of snuck up on me there. We're going to be studying next time what it means for points to have finite order. Like if I add a point to itself 4 times and I get the point at infinity or the additive identity, what does that mean geometrically? How many points of finite order are there? What does it mean if the set of all finite order points is a certain size, or if it's infinite or something like that? So that will be what we look at next time. So are there any questions I can take? You can either just type them in chat or unmute yourself or push to talk, whatever you want.
Anthony, could you say briefly what's the sheaf theoretic proof of the group law?
Yeah. So basically what you do is it degree 1 or degree there. I know it. There's just one detail that I want to make sure of before I say it, and I know right where to find it. And bundles. Right. So what you can do is you can look at all of the invertible sheaves on the elliptic curve. So locally free of rank 1. Okay. And then you can look at all the degree 0 sheaves. You can check easily that those form a group under the tensor product. And it's completely obvious that this is a group law. In particular, you get associativity very easily. Okay. And then you can check that this group law that I'm describing here comes straightforwardly from that group law in such a way that associativity is clearly preserved. So if you want the correspondence, I can give it to you. What you can do is this. You can say, so take an elliptic curve, EP. What's this P? This is the distinguished point. You can think of this as the point at infinity, okay? Then there's a bijection between the degree 0 invertible sheaves, mod isomorphism, of course.
Yeah, so basically
and then the set of all
you are identifying with the Jacobian.
Something like that, right? So what you can do is you can take a closed point on the curve and send it to the degree 0 sheaf. I think it's OQ minus P. Is that right? Let me see. Right. Yeah. And then you can also start with a degree 0 invertible sheaf and send it to the divisor of LP.
Yeah, but I mean, somehow you have to. I mean, you can do this for arbitrary genus curve, right? So, but it's special in genus.
No, and it's special for elliptic curves because the degree 0 sheaves form a group under the tensor product in this case.
No, they form a group under any curve, I think. But anyway, yeah.
Yeah.
I get the idea what you're saying.
Yeah.
Thanks.
Yeah. Yeah. And there's nothing to check with the associativity from this viewpoint. Whereas from the classical viewpoint, it's very hard to see this.
Yeah, but I mean, there is still a lot of other work you will have to do, I think. But anyway, yeah.
Yeah, I'm not saying, okay, so I'm being a little bit cute with this. I mean, there's a lot of work you have to do with schemes to even get to this point. So in that sense, there is maybe more to show here.
Yeah,
but if you're comfortable working with, if you're comfortable with the basic framework of schemes, then this is much easier than what we've done here. It's just a lot more machinery. That's all.
Yeah.
Yeah. Okay. Are there any other questions? Let me actually see one thing you said, Akaki. Degree 0. I'm actually going to look this up because you're making me wonder. Yeah, so invertible
But
sheaves
the-
always form a,
how they
okay, no,
define
okay, so the point is,
Jacobian of a
the
curve,
point
right?
is in general, the point is in general, you just have a group of invertible sheaves. But here
Yeah.
we're saying it's the degree 0 sheaves.
Yeah, so it's a subgroup of that group. I think.
Yeah, yeah.
And it's a Jacobian in general, which becomes a abelian variety, but in the case of elliptic curve, it's equals to itself, I think.
Right,
So
yes, exactly.
That's special
Yep.
thing here going on. Yep.
So like here in these notes I'm reading, you can identify closed points of E with this degree 0 invertible
Yeah.
sheaves without any work in the genus 1 case. Okay, are there any other questions? Oh, I got that correspondence right, actually. I'm surprised I got that. Let's see, I'm not looking at chat or anything. And by the way, last week when I was talking about special sheaf theoretic properties of elliptic curves, this is one of the things I was talking about. So you don't get this in general.
Right. So can we do the Zoom upload?
Yeah, or not, or
Well, I'll
whatever.
do it, but nobody else is doing it.
Yeah, yeah.
So what day are we meeting next week?
Maybe
So,
Wednesday.
I think it just.
I mean, I don't know.
Yeah, Wednesdays are a little better for me,
Right.
so we can keep doing Wednesdays. I
Okay.
think today was just you guys had a department meeting
Yeah.
tomorrow or something, right?
Right. So
I wasn't going to
Okay.
go to that anyway.
meeting.
Yeah,
Oh.
Charlie didn't have a
Yeah,
department
well, I'm
meeting.
sorry.
Yeah, he's fine.
Well, Charlie, we are counting on you to show up tomorrow.
Yeah, I'll show up in Kibitz, right? Send me a link.
I mean, I'll be there in spirit, so. Yeah.
I might be there in
All
audio.
right, well.
not in spirit.
Right.
See you guys later.
Bud might
Yeah,
be there.
so there's still a bunch of people in here. If you guys have anything, just type it out. Let me know. I'll be on here for a couple minutes. But thanks everybody for coming, and I'll see you
Yeah. See you next
Wednesday.
Ta-ta.